Ooh, good morning, everyone. How are you doing? How are you doing? It's a bit different than normal. I'm gonna try to change it up to make it good. It will require a little bit more practice, you know, a bit more practice. Anyways, this morning, or this weekend, I should say. Yes. Let's start with the weekend. Let's start with that, you know? Let's start with the weekend. What did I do in the weekend? Well, it's actually a bit inspired to make some things for you guys. And therefore, I actually made a few things, as someone might have seen. We talked a lot about Roundup last time. And let's see, open with Paint Explorer. Or that's the right one. Yeah, there we are. So we talked about Roundup last time. As an example, how GMOs are being used. And I thought of it and I was like, well, I can make this into an emote. A moving emote. And this is Roundup. It's the mice stays alive, but all the others die. That's what Roundup does. Mice have been genetically modified, so where it will survive the poison, while the others will die. And that's very simply shown what the reason is we have Roundup. Yeah, they have both the corn species, the corn variety, that has this that we've installed the genetic modification, so it survives, and all the other plants, well, all of them will die. This is the Roundup example. I thought I could make it into a actually simple little GIF. So that's how to make it, and I'm pretty proud of it. Yes. Now I have decided, since was some talk with the community, and well, decision has been made. It's going to be a Roundup without a without text. I'll start the text version, but I think it was a bit too much. Let's see. There, I think this one, well, it was a little bit too much in your face. A bit too much in your face. If you see it all the time at about this size here, roughly, it's pretty big. Then the plane already is a pretty big thing. So yeah. I think it's kind of cool. Maybe I should have made the little plants a bit bigger. Maybe. But that's in hindsight. I think it's kind of decent. It should be about this size. We'll see. It's very small, but it will convey the message, I think. So I'm pretty proud to make that one. And then I was on a spree. Because I also made... there's more. Which I don't think we're gonna do... We implement as is. This one. I like it. It is fun. It is actually doing what it should do, and it should. Maybe some of you notice that actually it's moving along, and also all the gene pairs are moving along with it, which is pretty fast to see. But I like this idea, and I made this, and I think it's a bit on the big side. Also, it's too fast. It needs a bit more, you know, a bit more relaxed to be good. So I want to make it a little bit slower than this, so we can actually follow it along, you know? Just make it slow and static. So I've been working on the next version, which, oh, by the way, if you want to see how much work it is to make one of those, this here, all of these, and this is what you need to do to make that one, that you're having on the screen right now, this one. You need all of these. And it's iteration 4 or 5. Of which I have to make all of these to test if it was actually good. And if I haven't made mistakes, which there might be some mistakes in there. But I haven't seen them yet. Yeah. Also, the gray background is a non-color background, so it could be on either the black background or the white background. That's also why I make the back layer. What do you call this thing? Phospholipid backbone? I think no, not phospholipid. It's the backbone. Phosphor backbone? I think it's a phosphor backbone. It's been a long time. But yeah, to make that gray so it's visible on both white and black. So that's just one. But now I'm working on another one. And as you know, until I can log in, I cannot use them. But, you know, I cannot log in right now, so I can't do that. So I've been busy working on this one here. As you see, it's only a part of the entire emote space, so it's not the entire length here. So it's less than your face. And I want this to move over slowly. I don't want this to move over slowly. I want this to rotate on the spot. It will stay here and it will just rotate. That's what it will do. That's the plan. Now, to make this slow means I need a lot more pictures. A lot more. So I've been working on that one for a bit. It's not done yet. That's why we're here. We need to finish it. Slow helix, there it is. I already thrown away 2 versus 35 of these pictures because they were not good enough. Actually, one of them were actually 3 pixels short. Because if I make this rotate in place, right? If I make this rotate in place, then there should be also things behind here that we can't see right now. They're just in between, you know? That just, yeah, you can't see them. But if I would do that, then they need to fit with the same size difference between them. That would look weird. Well, at some point the big opening would be over here, and this would be offset with 1 or 2 pixels, which would be awful. So I had to introduce all these 3 pixels here, so I had to remove the entire set and remake them. Also decided to go for double wide nucleotide chains, because 1 wide was just too small. It's going to be that size. And it's already really tiny. It's already really tiny, that size, you know? So, yeah, I didn't make it 3 wide because I had 2 or 3 bars only, which is not a lot, which is... I could look into that, but I believe it was not good look. Also, I need to readjust this, because this is all based upon 2 or 4 wide. That's what it's based on. Or multiples of 2. So I can't do 3 wide, I have to make it instantly 4 wide, which might be... You only get 1, 2, maybe 3 here, which is not correct. I could also make this one bigger, so it's only 1 opening, 1 closed one, and 1 open here. But that seemed kind of lackluster, because it is supposed that this is really long. It should be insanely long. So, yeah. I want to make sure that the feel was right. The feel had to be right. So I'm working on this one here. And that is the most of the plan for today. And we'll speak of the things we speak of, you know. So let's give me some water. Lots of talking happened. Okay, now, of course, it's been many years for me since I done much into genetics. So I'm rusty. I need some practice. So while I work on this, I like the figure side by side. Actually, I like that fact a lot. So I can't zoom in anymore on this one. So I'm just gonna put it to the side of my screen. Like that. Aha. And aha, there we go. It fits anyway. So while we have that, I want to see if I can also talk about, let's see. Actually, no, I'm gonna use the other, use one we used before. Yeah. We established this whole thing last time, right? Based on DNA, based on RNA, transcription example, and how to translate all that stuff into things. We talked about it last time. So let's go a little bit further away from this and go to a little bit more simple things. Oh, come on. Yeah. Sorry, that's a bit hard. So I think we can make a table, right? Just a simple little table. Something like that. Oh, well, that's all it. Not what I'm looking for. Table. Insert table. There we go. Haha. You want at least 3 by 3. Yeah. Yeah, let's start with 3 by 3. Let's start simple. Hey, some guy. Good morning, mate. Good morning, dude. How you doing? Let's start with that. So we have a few things that we need here. We have the parents, P for parents. We have the F1 and F2 and so on. Those are offspring. So Let's talk about homozygote, heterozygote. Sounds a good start. That's what I want to talk about today. Daylight saving hit me, so now the stream is a little later. Well, I'm also a bit late this morning. I need to prepare to what to talk about today. So, yeah. I'm also a bit late. It's my bad. Good morning, dude. Good morning. So, okay. Homozygote. Pretty simple. Pretty simple context. If you have genomes from your parents, right? You have two parents. Let's actually put this in the middle because it makes it easier. Actually, no, I need to get this away. This is the F1. Aha. Yes. Let's start with the basics. There we go. The parents. Well, let's ignore what kind of genome it's about. Let's say they've that and that for one parent, and the other parent gets that, for example. Yeah, there we go. There we go. What emote I'm making? Well, I've been busy in this weekend because I was a bit inspired by Friday. I just put them away. Let's put them back. So we're going to emote about well, the DNA, and I want this to rotate on the spot slowly. So we got these with all the measurements, so that we get it in the exact right spot. And I'm gonna make this pixel move to the left, or take one pixel away here, put one pixel back there. But then have to make every single of these base pairs go back one, so that they don't move. So he's actually rotating in the spot where only the curvature changes, but the base pairs themselves will not change. Sorry about that. Bit of hiccuping here. So that's what we're making today, and I'll come to that in a second. But also want to talk about this while we do so. Yes. So with the parents here, I want to explain the homozygote and heterozygote. Homozygote means so all gene copies, so that should be nice, yes, have the same data on the target gene, which means, for simplicity's sake, you have a gene for blonde hair from your mother and your father. On the same space in the genome, there's the gene for hair color and also says blonde. So both have blonde there. So both would be, for example, AA, for example. The letter doesn't matter. It only matters if you have a capital letter or a small letter. Is a I have to also go into dominant recessive genes then. That's also something I need to talk about then, because these are all the basics. I want to make this little file here, just out of all the basics of genetics here, while I do my drawing thing. So, okay, with heterozygote, the exact same thing. All the gene copies and all should be with double L, right? It's English, yeah. Dutch wouldn't be, but here it is. All gene copies have a different not date, data. Yeah, data. It's not a date, data. Yes. My typing is always perfect. So that on the target gene. So that would be that. And that would be that. There we go. Now here I make it very simple, where it is one one dominant gene and one recessive gene right here. Now dominant means I need to make a gene, right? Yeah. Actually, it should be allele. Only the same data on the target gene that we call allele. Is it allele or allele? I'm not sure. It was in English, probably different, right? Allele is in English. It's allele. Okay, allele. I also call it allele because that's the way you pronounce it, but so if you put this here, there we go. Yes. So the dominant allele always comes to expression. And doesn't matter. Also come to expression. And then put dots anywhere. So one here, and this here. Oh, it should also be allele. There, we need an E there. Make it good. I do want to have a space there. It's only expressed when no more dominant allele is present. Yeah, there we go. That's good. That's correct. And then we also have intermediates, but that's phenotype. No, we need genotype, phenotype as well. There's a lot of little words in there, you know, that they forget that exist. There's a lot of them. So genotype, phenotype. That will then be... Also, let's put a tab there. Just make it all the same place. It seems like a good plan. There. One further, so it will fit. Oh, there we go. Look how neat it looks. Look how neat it looks. Oh, man. Actually fancy. It's been so long to make things look neat. There we go. Genotype. Oh, we did put the space there. Yeah, I see you. And not that one. That one. Yes. Genotype. The So let's see. We got homozygotes. All gene copies have the same allele, same data on the target gene. So we call the target. We usually use the A's because it's easy. There's no reason to call them not B's or C's or Z's or whatever. You can call them whatever you want. We keep the X's and Z's. Sorry, X and Y's. X, Y, and Z actually for genetic. Not genetic. For procreation chromosomes. So usually you use those 3 letters, but that's for the entire chromosome. This is for the data on the chromosome. So yeah, I think I want to show this as well, right? Yeah, let's show this as well. So that would be then. Let's make it very simple. Let's make it very simple there, and I'll just do this twice. C. Ctrl V. No. Okay. Needs to be the same place. Use that tab as well. There we go. Okay, then of course we can't set it properly, can we? No. Yeah, there's offset there. Delete, and that's still offset. Why? Why? Oh wait, we use spaces. That's why. I know why. I'm dumb. That's why. Tab, tab, tab. There we go. And if I copy all that, C. There we go. And then we make this part all, make it, actually, easier spotted would be all yellow. Yeah, make out so yellow. There, yellow. And yellow. Core, there we go. And we make this yellow and red. Why not yellow and red? Why not red? There we go. And I think I want to hit the rest goat in the between, so we make it very easy to understand what's what. Take that away, delete that. Want to keep one enter there? Yeah, I do. There. That makes it slightly easier to understand. And of course, for people with who can't see properly, let's change this to that. Copy the entire thing. Control C. Control V. Dang it. Dang it. There, and here we do the same thing, because it's the same thing anyway. There we go. But these here will then be some other symbol. What do we take? Let's take that. That. So it's visible both color and in form. I think that's good enough. I think it'll work. Yes. So we got homozygote, heterozygote. Correct. Yes. Dominant allele. I think genotype phenotype has to be above, right? Because this is more the overall arching idea. Put it there. Yeah, that seems better. So we talk about the alleles present in the current organism. That's genotype. Phenotype, the alleles expressed in the current organism, environmentally dependent. So this means you only see the dominant trait. For example, if that would be dominant here. Actually, if it's here in letters, yeah, double A. So in this case, yellow is dominant here, if this is correct. So in this case, you would only see yellow here. So this would all have the same if it is hair color and this is blonde, then this would all be blonde hair color. And you wouldn't see that this one existed. You would not see it. It would be like it's not there. Is this one offset? No, it's correct. It's correct. So we got that one. We can take away one of these there. Good. Do we put enter here? Yeah, I do. There. Nice and fancy. Let's save that. Good. So then we have dominant alleles and recessive alleles. Or dominant traits. I could give it a trait. Makes maybe easy to understand. Do we need to do it twice? Don't really think we need to, but there it is. There it is. Good. Good, good, good. I need to sniffle a bit. Sniffling. Camploy, I'm muted. I feel stupid. I explained so many things. How do Camploy? Good morning, mate. Oops. Uh-oh. That was dumb. Anyways, I'm trying this setup here. I'm working on emote. Let's show it to you, because I haven't shown them to you yet. I don't think so. So let's see. We're working on emote. I've been inspired by last time, by Friday. Where is it? So I got myself a moving helix because I thought it was cool. Open with Explorer. There it is. I made this one. And I like this one, and I even made sure that all the alleles, or all the... sorry, not alleles. Wrong word. All the nucleotide pairs, which these are, actually move along with the chromosome, but it's a little bit too fast. For if you go to about this size, I mean, it is... They have enough space, I guess. But I think it's a bit too fast of that thing. I don't think it really... I'm not sure if I want to keep this one or if I make it slower. I think it goes a bit too fast. And as you might have seen in the Discord as well, because I put the others one in the Discord, because I had a question about those. So that's basically a DNA strand, two DNA strand thingies. And I got myself a roundup version, which I made 2 of. I got them with text, which I also made this weekend. Because we talked about this last Friday. We had roundup, which then would kill all plants, and then we had genetic modification in a species of varieties of mice or corn, and that would then not be affected. So this is basically the picture on what Roundup would be on the field, which I think pretty much states the point, right? Looks awesome. Thank you, dude. Thank you. It was a lot of hours of work, so I hope it looks good. I think in hindsight, these plants look a little bit too small. If you make them about there, it's a bit small, but you know, it kind of gets it. Although I think I made another one because I wasn't sure about these letterings, right? These letterings seemed maybe a bit too much, so I made this one as well without the lettering, and I think this one is just simply better. But that's my personal opinion. I put a poll into, or put a question in the Discord. But yeah, I also asked some friends of mine, and they're good. I love the fact where I put a few of those little drips just go past. It's a very small detail, no one will see it, but I like that. It's simple. Yeah. But this is simply the roundup story I told you last Friday of. And I was like, I can make this into a GIF. I can. So I did. Now, I still can't log in, so I can't put it as an emote yet. But when I get the chance to log in, I will put it in as an emote. Yes. So yeah, that was fun to do. It could be kind of small, but it looks great also. Yeah, thank you, thank you. I'm not the best artist, but it is kind of... does it look like a plane? I think it looks like a plane flying over. I think it does what it needs to do. You know? I think it's okay. For just a random non-artsy guy trying to do some things, I think it is pretty cool. I think I like it. But yeah, these are made, and I probably stick with the no text one, because the text is a little bit too much in your face, I think. Even though I actually put it from down to up and also make it bigger and capital letter stuff in the middle. Little details and stuff to actually see that the plane was moving towards, over, and past you. I like the idea still, but I don't think it really works. So login problems, SIM card issue? Yes, I do. I still need to get my finances such that I can actually buy a SIM card, which is only €2. Yeah, that's a problem for me. So my finances are a problem, man. They're a mess. But it's been that way for years, so yeah. Anyways, I will find a way. Life will find a way. I hope. Anyways, I've been working on these, and I do like this one. I think I want one of these, but on smaller. Actually, what I think I want, is to make a slower version than this one. This one is too fast for me. So I want to make, let's see, that's what I'm trying to do today, but it's a lot of work, so that's why I want to do it on stream, because I just don't have time to make it all. And there it goes, and then slow helix, there we go. So what I want to do, I made another helix structure. Actually, we had a picture up already, didn't we? Yeah, already had it all set up. Well, kinda. You need to go there. Actually, you do that and that. There we go. So I made a new version of the DNA strand. To make this one, I want to take 1 pixel away from here, put it on the back, put it over here, and then make all the alleles, I keep calling it alleles, all nucleotide pairs, yes, difficult word, back again. So these won't move, except moving, rotating on spot. And this one, this curvature will move forward slowly, and then actually turn the things around. So this is the current setup. Good setup for the alleles. I said it again. Nucleotide pairs, yes, those things. Also made some that can actually fit in between here. I made a set of 34 of these, pixel by pixel, over the weekend, and I had to delete them all because of these here. I didn't think of that. At some point the curvature will be on the highest point over here, and then there would be more nucleotides over here, and that it didn't fit because I had one pixel too few here, and here, and you have an offset one, which is unacceptable. So I need to make it from scratch again. So yeah, that's where we're at. That's where we're at. And while I do that, I want to give you some information and talk about the genomes, and just give a refresh of the basics. It's been many years for me as well for all the genetic stuff, so I thought I'd just do a little bit of a refresher for myself and you in the process. So I wrote this down for this morning. We went over genotype and phenotype, went over homozygote, heterozygote, dominant alleles, recessive alleles, and intermediate phenotypes, and ploidy. These are the basics, because we're going to do a little bit of an exercise, just my own personal small puzzle, personal small puzzle. This is the basics for any kind of genetic stuff. You should know a few of these words. So genotype are the alleles present in the current organism. I should put down allele as well, right? Yeah. Allele. Let's put it there, and then we put a bum, right space. I think it is. Let's see, the information on one gene in the target organism. On one of the targets, yeah. There, how's this? The information on one of the target genes in the target organism. Sounds complicated. So you got an organism. Let's make it diploid for simplicity's sake. Has two alleles right here. Same chromosome, same location, because that's where the gene is. The location is where the gene is, and both the mother and father varieties, or mother father of this organism, had the same information on that allele. Yeah, so these was our alleles, and they're both the same in this case, and they're both different chromosomes. Chromosome of the mother, chromosome of the father, or the other way around, doesn't matter. So, and here you have two different alleles, different information on the same chromosome. So for simplicity's sake, let's say this is eye color. The color of your eyes, which I talked about Friday, is on more than one gene, but let's assume it's on one for simplicity's sake. Also makes calculations a lot easier. So if this would be let's see, in this case I made it this, so this is both dominant, means that it will override any less dominant trait. So this will be brown then, and then this will be blue, for example. So here you have pure brown eyes, dark brown eyes. Unfortunately with brown eyes it's intermediate phenotype, but let's assume it isn't. So this one should also be dark brown eyes. Not correct, because with eye color it is an intermediate phenotype. Both blue and brown have similar dominances. It's right here. So both varieties of the alleles, the information, have approximately the same dominance. The dominant one always comes into expression. The recessive one is only expressed when there is no more dominant allele present. So this one you could not see in a lot of cases. But in intermediate phenotypes, they're both roughly the same dominance, so there is a result. If you're someone with light brown eyes, it's actually intermediate phenotype between blue and brown. They have both the genes the alleles for brown eyes and for blue eyes, and then you get light brown eyes. Yes. Have you got a new SIM card? No, I haven't yet. I need to go to a store where I can buy those. I need to go to the city, which I haven't been in a long time. Actually, the problem is in the city we don't have SIM cards. They don't sell them there, so I need to buy them on the internet. The problem is that I need to buy them with my bank account because they will not accept normal coins over there. And the problem is then that I can't buy anything on my bank account because that's in the red. So yeah, it's a problem. In a month or two, I should be just above, just in the black again. Then I might be able to do it. So if the shipping cost not too high, we'll see. We'll see. It will be a while before I can do that. Yeah. Finances are bad on my part. So yeah, this is the basics of genetics here. So I talked about alleles. That's the information on the gene. So information on the gene. Should I also just explain about what a gene is? I think yes. I think it's important. We need to get all basics. What is a gene? Occasional chromosome. Specific location on the chromosome affecting a certain trait. This is, for example, if you have a let's paint again with an empty one. This one, yes. So if we have our beautiful chromosome here, one chromosome, it goes into basically infinity. So infinity, there we go. And we have another one right here. There we go, and make it look like it's infinity. There we go. And you're looking for a specific gene. Here we're looking for, in this case, we're looking for. We said eye color, not the best example, but we'll take eye color still. Then we're looking for a little spot. Nope, that's not. That was too fast. I should first have let it go. Let it go. That's about the same width. Yeah. There. Let it go. There. There. Yes. Okay. And then we're looking for. Let's make it also yellow. So, for example, it will be here. This is on the. There it is. And there it is. Very nice. And I'll take this. Oh, it's not the same width. Dang it. You know what? Screw it. Copy the whole thing. There we go. And then we'll put it down there. There we go. So, we have, in this case, a being, let's say human, let's make it simple, diploid, so it means we have two chromosomes, one from the mother, one from the father. On the same location, there is a gene. This is the gene. This is the gene about, let's say, eye color. For simplicity's sake, it will be eye color here. And let me see there. Beautiful. Is it with OU? I think we'll just O is enough. Eye color. Oh, this is eye color. So we can say of this one, on this position, on this gene. So this is gene. I don't know. Make up a number. Make up a number underneath 23. Let's make it 6. I don't know. It could be anyone, but this is chromosome 6. All the other chromosomes don't have this spot. But only chromosome 6 has this spot, and you have 2 of them. And this one is actually. Let's make it a. Here now it's heterozygote, so now it has the color for the eye color here for brown and for blue. So in this case, because eye color is one of those intermediate phenotypes, they're both roughly the same strength, so we get a light blue-eyed person with this one. Sorry, a light brown-eyed person with this one, and this will be a blue-eyed person, and this will be dark brown eyes. Yes, there we go. Read both. Maybe check your mails because the alerts might not work right. Mails? Okay, let's see. Alerts don't work. Mails. Let's see. Mail. Oh, dude! Dude, you're awesome, man. Thank you very much. 50 euros. Dude, you're awesome, dude. Thank you very much. You are amazing, dude. You are the best. Thank you very much. Yes. 50 euros, dude. Thank you. You are the bestest. You made my day. I need to get myself a new SIM card this afternoon. Yes, yes. Thank you, dude. You're awesome. I don't know why my... It's probably because I'm not logged in, is it? That's probably why it doesn't work. I do have your stream streak from 70 minutes ago. Why doesn't that work? Let's see, maybe that should be in stream elements. But dude, that's so awesome, dude. Thank you very much. Thank you very much. Oh, I can't log into that because it's also Twitch. Dang it. No, I can't log in. Nope. That's why I can't get my alerts. Because it's also login issues. Yes. Now we know. Now we know. Best I can do. Dude, that's so nice of you, man. That's so nice. Thank you very much. You are awesome, dude. You are the best. So, yeah. So I explained about what the genome is, what a gene is. That's one place on a specific chromosome with information regarding a single trait. Is that understandable from this? I think it is, right? If it's English, it's color, but Americans were lazy and didn't want to pay as much tax on the ink for printing newspaper, so they started to drop characters down to color, but we ignore them. Ah! So I'm now actually someone who would... No, that's not it. Now I'm actually someone who would actually put glorious tea into the harbor and spoil it. No. We're not America here. No. No American. Here. Wait, it doesn't work. This one needs to go. This one needs to go. We can't be American here. We need to be properly English. With tea and stuff. You know, we don't put tea in the harbor. We don't. Tragic happened. So there it is. No one ever saw this. So there we go. And now we nicely put it there like that. Yes. Beautiful. Trust me, you saved me. We're fancy again. There we go. Eye color. There we go. Such as a needless waste of tea. Exactly. Needless waste of tea. How could you do that? Definitely better in your mug? Depends. In your mug or in your mug? Suddenly someone thrust the tea inside your face. Ow. Yeah. So, we got the genome here then. I think that kind of sets how it works. I haven't done anything on the emote yet. We still need to do that. This is all set up. This is all set up so you understand what we're doing here. Yes. So I talked about alleles. I should make them different location because first you know what the gene is, then you learn what the allele is because allele is on the gene. Yes, that seems logical. There we go. So gene, specific location on the chromosome affecting a certain trait. Seems obvious. Allele, the information on one of the target genes in the target organisms. So that would be the information on that gene. That's a lot easier to actually say. I have to make it specific gene because we are talking about two different genes here. We're talking about the same gene on two different chromosomes here. So this one is different information than, well, in this case, this one. So it needs to be a specific gene, yes. So that's the allele. We got genotype, the alleles present in the current organism. Yeah, the alleles present. It doesn't matter what if they're dominant or the recessive, doesn't matter at all. Just what alleles are present, that's your genotype. Do you have a brown eyes allele and a blue eyes allele, then you have both of those, none of them get ignored. The phenotype, however, the alleles expressed in the current organism, environmentally dependent. This is a far bigger thing than most people think. Often people say, I have bad genes for whatever the hell. 9 out of 10 times it's the environment or the way you're raised or stuff like that. That influence way more than most of your genes do. People think it's 80-20 for genes versus environment. It's usually more around 40-60, where environment usually is the 60%. Yeah. Anyways, we got homozygotes. All gene copies have the same data on the target gene. I say all the gene copies because, as we discussed before, we have ploidy, where you have monoploid, which is weird. You have diploid, tetraploid. I know of leaks are octoploid. Octo. They have 8 copies. Yeah, that makes this a lot more complex. But let's not talk about that yet. Those things we'll keep for later on. They're not here yet. We talked about how eye color is one of those things that have an intermediate phenotype. If you have the allele for blue and the allele for brown, then you have light brown eyes. That's intermediate. That's not one or the other. That's a little bit of both. A bit more brown, but you know, it's intermediate. It's in there somewhere. Dominant traits always comes into expression, written as a capital letter. Recessive allele is only expressed when no more dominant allele is present. So oftentimes you will not see these things. Oftentimes you would see, let's take something random, a random example. Let's say hair color. I don't know if it's correct hair color, but let's say hair color. Black hair is dominant over brown hair, let's say. And if you got a, I need to go into this. Yeah, why not? Let's say you have 2 parents here. Let's go to our Asian parents right here. Let's start with the actual important, funny, cool stuff. This is my crossword puzzle. This is the thing that I love to do a lot. So, these there's a name for these as well. These are basically the cells for procreation. Inheritors? I don't know. There's a word for this. I forgot the name. It's been years. As I said, it's also for me a fresh up. So, if you get 2 parents, these are the parents. The parents, actually, this is what the parents are. So should do it differently. This is what the parents are. The parents, we got 2 parents here. We're talking about hair color. So let's make this little thing. Let's make them human parents. Obviously human parents. Yes, they are human. Both have black hair. Let's call it black hair, and we've done change these ones into that. Both have black hair, and let's say the black hair. Let's say black hair is dominant over brown hair. Okay. And so both parents have black hair. Black hair is dominant over brown hair. That's what we assume here. So here we get into the offspring. Now, if we have offspring, let's do it in letters. Let's also make this all middle. Let's see, it's just nicer looking. There we go. So we got a few children. Let's say they have 4 children, just for ease, just for simplicity. This one has black hair. This one has black hair. This one has black hair, and this one has this one. If they all have black hair, if all of them have black hair, right? And there's only 4 children. They all have black hair. Then what can we assume of the alleles in the parents? Now, we got the father and the mother. Doesn't matter on which side you put either one of them. Doesn't matter. So for black hair we need, it's dominant. So black hair is a big letter, a capital letter. Same thing here. Also needs to be also in the middle there. There we go. They could both be homozygote or heterozygote. So they could have this one, or they could have this one. This one. So we need to determine which one they have. So for now we don't know for sure, but we find out that when they have a fifth child, that one has brown hair. Is that how you should write fifth? Probably not. There we go. Fifth child had brown hair. Has. It's probably not dead. It's probably not dead. Let's assume that. Let's assume it's not dead. Yeah, fifth. Yes. Human? No. Human. Human. With Ferengi here. It's humans. It will always be humans. Yes, I'm old. And I still think it's funny. The fifth child has brown hair. What is the genotype? What's the genotype of the parents? So, let's say... So how would you go about this? You do know that at least one parent has a black... the genome for... Sorry, the allele for black hair. You know the other parents could be... they both have black hair. They both have black hair. So they both have the capital A. They both have that one. Let's say black hair. Let's do this. That makes it easier. Should write down what these things are. For brown hair. There we go. These are the letters we can use for these alleles. You could make them any letter you want, but it's usually use the A because it's simple. Okay, so we do know that they have one allele of black hair each, because black hair is dominant. You might not even see because dominancy here. Always comes to expression with this capital letter. Recessive alleles only express when no more dominant allele is present. Yeah, so in this case, for the fifth child to have brown hair, the only genotype it can have is two little A's. Let's do that between brackets for easy to read. Because if it had one capital letter from either parent, it would be black haired. So it needs to have that. Now, if we get these two parents and they can get either one or the other, or one or the other, then for these parents to make a child which has brown hair, in this case a recessive phenotype, that means that we do need this result somewhere. That means we need one small one here and one small one here, and that makes that they have this, not S, this option. You also put a dominant one in front, doesn't matter from which parent it is, so we don't have to swatch them up. This is incorrect, this must be that one, yes. And we have that one. Yeah, that is correct. So you can have the genome, not the genome, the allele from both parents. They have to both be heterozygotes. They both have both have different copies of the allele to actually make one child which has a full recessive genotype. Are you some Ferengi geneticist that's going to alter the human race? Of course I am. For profit. For their benefit, yes, definitely. For their benefits. At gold press platinum. We're gonna sell them. We're gonna sell them. Probably we're gonna make a company with a big apple on it. And we're gonna sell them the same things they can get for much cheaper, but only from the apple race. And only the apple, we make special things that can only work on the apple, and they cannot use other things. Yes. That sounds like a real good Ferengi thing to do. Yes. Apples. Apples are good. They think apples are good for them. And we just earn oodles of money. Yes. Yes. Anyways, this is a simple example. This is one of the simplest examples you can get. And in this case, the answer would be that parents have Heterozygote. So here we go. Parents have heterozygote phenotype, right? Oh, that's okay. I'm not on Apple. Very good. Gameplay is worried. Gameplay is worried here. Yeah, you should be worried. Apple is a scam. Apple is a scam. Absolutely. Simple example. This is why I hate Apple so much. It has been proven already that Apple, you know that you get updates every once in a while on any kind of device for all kind of reasons, security or for drivers or whatever. Apple actually put updates on Apple phones that make Apple phones go slower over time, purposely for that one reason. Because then you buy more phones, because your phone becomes slow, and eventually, oh, I'll buy a new one in 2 years. That thing could work for 15 years perfectly, but they actually sabotage it so you buy more of them. That's what Apple does. Also, what Apple also does is try to make sure that you have to use their kind of power cords and their kind of whatever accessory you need to fit it, especially charging wires, and make them 4 or 5 times the price of any other charging wire in the world, because you have to use theirs. They're trying to create a monopoly, and they're getting pretty good at it. They don't give anything more. They don't give anything more. If you take a PC, a normal Windows PC, you can do way more on it than you can do on Apple. For example, gaming cannot be done on Apple PCs. Surprise! Yeah. Apple is stupid. Apple is stupid. So I don't agree with Apples. Apples are bad for you. But in this case, we got some information down. Do you get all this? Is this too much? I hope it isn't too much, but because I'm going to give you a problem, and you need to solve it, chat. Yes. Well, I'll do some actual work here. Yes. So we're going to look into a little thing, into a family, a random family. Let's take, yeah. So we have 2 parents. So we have the F1, the P, the first parents. Then we're going for the F1 and the F2, I think. So we have here, with all the information you got here, right? I do need to make one more thing to this. Can I copy and paste a thing like that? Can I paste that? I can, yes, good. So, this is for numbers calculations. If you have, and we always assume we have a big population, that's how you use genetics, because on single term basis, it's really hard to determine how things go if you have only one set of parents. So assume you have 1 million parents, and then you can make calculations in percentages. So in this case, when you have these parents here, we got this whole thing solved. This will be 25% of the offspring. Same will be here. And here. And here. No. Don't change my lettering. No. Bah, don't change my lettering. There we go. So, if we get an offspring from these parents, and if there would be a lot of them, then we have 25% chance to get a homozygote black-haired person. We get 20% to get a heterozygote black-haired person, but another 25% as well. So we get 50% chance to get a black-haired heterozygote person, and we get a 25% chance to get a brown-haired homozygote person, right? So how we write this down would be 1 in 2 in 1. 1. This would be how it would be divided in the genotype, in the phenotypes, and also genotype in this case. Because you would see, actually no, this would be only phenotype. Never mind, I'm done. So this is only genotype. I'll remove the wrong one. So you would have 2. So you would have 1 of 4 having homozygote dominant, 2 would be heterozygote, and 1 would be homozygote recessive. Yeah? Gaon type. There it is. Genotype. There we go. The phenotype in this case The phenotype. Writing is hard. The phenotype. Actually, let's put things in between for easier of reading. And you. I like my arrows. Arrows are cool. Arrows are cool. If you disagree, then, well, you disagree. Very simple. It's got a genotype like that. And the phenotype, well, we see three people. And 3 people with black hair. They all have dominant traits here. Those 3 dominant traits. Let's make them... let's copy this again, just for ease of spotting this. That's not it. No. There we go. So we got the genotype. Let's take that out. And let's make that thing green. Make that thing let's say bluish. It's hard to see, right? Let's make that yellow. Why not yellow? And make that one red, just for ease of spot. That's the wrong one, not that one. Let's make it this one, black. Well, black won't really work, right? Then we can't read it then. There we go. So that means this one is red. This one will become yellow then. Yeah, yellow. It's really hard to see down there, but that's fine. That's fine. So this part, this part, hopefully you understand this part. The genotype is 1 and 2 and 1. That's the genotype. The phenotype, however, let's take that away. There, and I have to take this away. That is the answer to this question here. There we go. So the phenotype is 3-1. That would then be this one we make green, more green, more green would all be black-haired children, and this one will be the brown-haired child. So let's make it actually, yeah, I'll make it red. There we go. There. And we take the green there. You understand this phenomenon? On lunch break, can't solve problems while clocked out. Don't worry about it, man. Just let your brain fill with information then. That's fine, that's fine. So these are some basic concepts. And if you know these numbers, I know from top of my head that you get 1-1 and 3-1 in a heterozygote parents couple. Because these are just standard things. These are the simplest starts. So let's see the problem I'm gonna put in front of you. And this will be slightly more difficult, because that's fun. It's fun to challenge people, I think. So the parents. Infarct. Is it an infarct? Is that the right word for it? It says yes, okay. One of parents dies of brain infarct. Two. Actually, it's the other way around. Doesn't really matter. How much chance? Let's see. One of the parents that dies brain infarct is 2. 2 of 3 siblings die due to heart infarct. Last sibling gets a brain infarct. Chance does F2 of 5 to get an infarct. Infarcts are basically you get a blood clot somewhere, and that goes to a place that has a problem. So it could go to your lungs, to your heart, to your brain. It could also cause problems. It could also go to your leg, and then it doesn't cause any problems. But infarct chances of dying are pretty high in this family. So we're gonna solve that. So we call this infarct because infarcts are deadly. That usually means it's on a recessive gene. Because if it would be a dominant gene, far more people would die, and actually the gene would die out. So A allele. So it should be a small one. Don't make it look bad. There we go. A is the infarct allele. We know that we got the parents here. The parents here have, at least one of them has a small a, and because it's a recessive allele in this case, that means that to get an infarct, one of them has a homozygote. Let's put that down there. So one of them must have a homozygote recessive genotype, while the other parent, who did not get an infarct, must at the very least have one of the genes as well. It could be that it has both, and just haven't been seen. So let's do that. Yeah. So one of the parents dies of a brain infarct, so it has a recessive full set. The other one is not dead. You haven't seen, but because infarcts are not 100%, it might be also a recessive gene here. It might still happen. You never know. So we still have at least one extra recessive trait here. So this is the parent population. Then we copy all this thing. Actually, copy this thing again. That would mean that we have here. Let's empty all this out. This and this, and make that a small one. Actually, put a question mark here. Why not? Then a small one and a small one. So we get question small, and we've got small, and small. Don't, stupid auto. No. Keep it small. There we go. Here's what we know. So from these parents here, the grandparents basically, the first parents, let's put it in, actually put this in the middle, as it should be, in the middle, there. So we got this from the parents. The parents have the recessive trait. They have a 50% chance to give that to their offspring complete, and a 50% chance to give the question mark. Might be a safe one, might not be a safe one. So the what do we call these things? Verhoudingen. I forgot what you call these things. So we have here a genotype of 1 to 1. You always try to use the lowest numbers. You could say 2 to 2, but since they're all the same, we can make it into 1 to 1. So 1 to 1, with one being fully homozygote recessive gene, and one being unknown and one recessive gene. So might be heterozygote, might be also homozygote, we don't know. So genotype 1 to 1, also phenotype 1 to 1, because nothing has changed. They're they're the same. So we know this now. Now, if we crossbreed the F1, or if we take the F1 with someone from the populace, then let's assume that the populace overall usually has the dominant trait. And the recessive trait we can make rare, we cannot make rare, we'll see. So we have, in this case, we take one of these here. So we make the double cross again. Let's copy this, yes. Take that down there, we're going down, and we take that down there. So we have here, this needs to all be empty. Ah, no, that's not it. Just hope to empty it. There we go. So we got one of these we combine with the populace. Let's assume we know that that all 3 of the siblings here had an infarct. So they're at least, so every single one of them must have had the pure recessive set of genes. None of them got the unknown one unless the unknown one is also the recessive gene. So therefore, we can assume that all of these offspring of the original parents have homozygote recessive gene pool here. That's all they can give. That's all they have. So we can assume that we're dealing here with small a and small a. And from a general populace, we can have, usually, let's assume that that is a rare trait here. So most people would have a dominant trait at least somewhere, and we don't know about the second option with the parents. So it could be a dominant homozygote dominant. It could be heterozygote. So if we take this, we do have a chance to get a safe genotype. In this case, the children will not have any kind of infarcts in their life. And we could have question mark and we could have question mark and recessive gene, recessive allele, not gene. I say gene all the time. It is an allele. Yes. Let's take this thing away. How am I muted? How? I didn't even press the button. I was muted again. Dang it. Damn it! All my explanation gone again. Why? The thing, I have here a button with a light bulb. Light bulb next to it. The light bulb goes on when I'm muted. The light bulb was not on and I was muted. Why? Why? Anyways. So, we got this problem here. I'm not sure from what point I was muted, so let's continue from the start. For the ideas, yes. So, we got a problem here. One of the parents dies of brain infarct. 2 out of 3 siblings died to heart infarct. The last sibling gets a brain infarct. Infarcts we'll just treat as one singular trait. You get an infarct or don't get an infarct. Very simple. I know it's a lot more complex in the body itself, but we can calculate with this. How much chance does the F2 offspring, the second generation offspring, have to get an infarct? The small a is the infarct allele, recessive allele. Because in normal populace you expect a allele that kills someone to be recessive, else would be removed from the gene pool already. So with the first cross here, we know that one of the parents dies of brain infarct, so it has homozygote recessive genes here, homozygote genes that allow for infarcts. The other parent must have at least one of the alleles to be the recessive infarct allele, because else the siblings, the offspring of them, couldn't get brain infarcts, else they all would be without brain infarcts. So then what follows is that we know that the F1 gets at least from one of the parents gives 2 recessive genes, 2 dangerous alleles here, while the other parent gives 1 recessive at least and 1 unknown. That's why it's a question mark here. And we copy that and we see, and we work this out, and we see that the chances are 1-to-1 in genotype versus unknown and infarct, and always infarct. And phenotype, same deal, because we do not know what this does. We don't know. So then we combine that into the F2. Now in the F1 we know that they all have a heart infarct or brain infarct. So they all have this genotype because they had infarcts. Therefore we can assume that if we get the F1 into F2, we get the parents of the F2, at least one of them has a full set of recessive, homozygote, dangerous alleles. You get an infarct allele. Of the general populace, we take another individual, and in the general populace, if there's a trait that kills, that's usually a recessive allele. Else it gets usually tossed out of the gene pool itself because it dies at some point before it can reproduce, and then it just dies off slowly over time. So we can assume that the new incoming parent has at least one no infarct allele. We can assume that. The other one we don't know. We don't know if the other parent is homozygote or heterozygote. We do not know. So from this we can confer that we once again have a question mark there, but we do have a 50% chance of having safe children with no infarcts who can give it on to their offspring but don't have them themselves, so no infarcts there. So genotype 1-to-1. And depending if the second parent has a recessive gene or not in the second slot, it can be either infarcts or no infarcts at all, because she could be having a safe allele here, in which case none of these would have any infarcts; they will all be the exact same. Or we could have recessive allele here, in which case the 50% of offspring would get an infarct. So phenotype-wise, we could also want 1. So phenotype-wise, and because we don't know if this should also be OR. There we go. So OR. So we have in this phenotype here and genotype here, we have a 100% chance that they get no infarct, or we have, that's the one here, or we get a 50% chance that they get infarcts themselves. And for the phenotype, that's the exact same thing, because that's the thing that shows. So this is actually my family. This is something that runs in my family here, and this has all happened. So we now know that in my family, the chance that I get an infarct in whatever location is, it's just a blood clot somewhere that will knock me out or do something nasty to me, is a either 50 or 100%, 50% or 0% chance. Now I already know for myself that I had an infarct. I had one. I was just lucky enough to know where to put it, and I made sure to. You can feel it in your veins. You can feel a little blood clot in your veins, and since I know a lot of biology, I know a lot of the bloodstream. And it's starting in my left arm. Usually it starts on the left side of your body. That's usually where it happens. And I was able to manipulate it to get towards my leg and become problematic. So become without a problem. You have a lot of veins in your legs, which you can do without. If you get a heart infarct or you get heart surgery and you need to get another vein, they usually take a vein out of your legs because you have a lot of them there. So I was able to put it in my leg, and it either dissolved there or it blocked it for a bit. But that I got out of that unscathed. So we do know that is one of the grandchildren of the original populace that has a infarct. So do know that in my family at least, there's a 50% chance to get infarcts in the current generation. And this is how you find out things about your own family. This is how you can actually calculate for yourself. Hey, there's this in my family. There's this thing I want to know. What do your grandparents have? What do your parents have? And their siblings have? And you can calculate what you yourself have. And this can be for, or in this case, infarcts, or this can be for all kind of things. So yeah, if you want to know anything about what's in your family, this kind of information you can just put together yourself, or you can ask me to do it. And you can calculate how much chance you have to get X. Also know there's also chance. There's no guarantees. Even if this says 1, there can also be other circumstances, because as I said, genotype allocates for approximately 40% of what happens. Phenotype, the environment, does a lot more. Does usually 60%. So you can still be completely safe and healthy even if you have a double set of infarct genes. And infarcts are a lot more complex than one gene set, so there will probably be a dozen or so different alleles involved in this. So, and some might be dominant, some might not be dominant, so it's not that simply cut. But percentage-wise, on big numbers, this holds true. And gives you a little bit of an idea. And I now know that I need to watch my brothers, because they all have a 50% chance to get infarcts. Yes. But I love to find out these kind of things, these kind of little things that is just hard to find out. I could have done with the size of your nose, or I could have done with the hair, with the color of your hair or eyes, or something like that. You know, you can do all kinds of things with this, and it's just awesome to find this kind of stuff out for yourself. You can do this. You can do this. All you need to do is know. All you need to do is know. So yeah. Anyways. If you have any questions about this or any kind of things that you want to know how it inherits in your family, we can calculate that. We can calculate that. So, well, you can think of that. I'll do a little bit more of my work because I haven't done anything yet. I still need to start working on these ones here. Yes, that was the whole plan. Originally. I haven't done shit yet. Also, the alarm. I'm not sure if you can hear it. It is not picked up. Good, it's not picked up. Good. We're safe here. We are safe. There we go. First month of the month, they test the... Actually, yes, I can do... that is a problem. That's gonna be a problem. No. Just... There we go. Then we can at least probably manipulate it. I cannot touch it. Oh, there I can. There I can. It's not the right way. We need to have that select transparent. There we go. And that seems correct. And then we place all this back. 1 pixel of every side. There. Wait, we do have. We're not. Oh, we do have white with us. Why? Why do we have white with us? We don't need that. Unnecessary. There we go. There we go. Okay. Now we need to move every single one of these. One to the left, right? Oh no. No, one to the right. Because I moved the entire thing to the left, so these need to go one to the right. Yes. Okay. I thought I did it wrong the first few tries. Yeah. I thought I did it wrong the first few tries. Okay. We're gonna take red. Why not red? Put it there. Not that big. Let's make it slightly less big. There we go. Let's make it the right size. There we go. Just take away that one. Big on Satan. And a bit of green. We're just gonna put them all at the right place. And put you there. I'm not muted this time. Aha, there we go. This says to be red is on the bottom of this one. That's why I have this in top here. So we want to put this one to the side here. And red is slightly longer than green. So red is slightly over half, or green is slightly under half. That's the whole plan here. But it does rotate and do things, so it will look a bit different.
This I have to do about 30 times until we completely turn this whole thing over, at least once. So this will be a lot of drawing here. I need to do this, I think. Is it too dark here? We'll see. Yeah, it's lined up. Hey, it is lined up. The sun is here. I can see things. So yeah. Yeah, I like the genetic things. I think it's a lot of fun to find things out. And this was just a puzzle, a small one. Not perfectly accurate one, but close enough for me. We can actually see how things will affect you in the future, or affect me in the future. Let's see. There we go. Yes. And we need one of these. But then I love to do these kind of puzzles for all kind of crops. There were I've done it for tomatoes and for all kind of things. And you usually look for traits that give them a higher yield, or to make them resistant to some kind of disease, stuff like that, you know. That's why I use this kind of information for this kind of calculations. And then of course, because you can have 10,000 plants, 100,000 plants, you can actually use calculations, and they're actually pretty accurate. And you can then make sure you get the best kind of a crop that you can get with a specific parents group, which is kind of fun to do. You see, Victor Ambrose and Gary Rookvan won the Beeple Prize in Physiology or Medicine for their work in microRNA. I did not know. Oh, I did not know that. Ooh, I need to look it up. I don't know much about the prizes. For me, it's been a good amount of years ago since I did all the genetic stuff. So I'm a bit behind on the knowledge. But should look to it, because that's kind of interesting things to see. And that's because my knowledge is a bit outdated. It's about 10 years ago, So there will be a lot of things that I don't know. So I can learn a lot more new things now, which is fun. Because I like learning. Learning is fun. So yeah. But I need to look it up. What do you know? What they were? What they did for their Nobel Prize? Oh, sorry, the Babel Prize. We were on this part here. Yes, we were here. What did I find out? Some kind of new sequencing method. I talked with some people years ago about different types of PCR. For those who don't know, PCR. What PCR is I forgot the lettering, what they exactly mean. Actually, we have Google. A PCR. Let's see. Polymerase chain reaction. That's it. Polymerase chain reaction. Very simply said, you take some kind of genome, some kind of squiggly boy, and you say, I want to know more about this part here. That part. No, it doesn't work if we have fill there. No fill. There. We know more about that part. So you're going to look into that part and find out the code and find out, hey, where can I cut it? What are the start and end points of that? Where can I cut it? So you put in a scissor. Put in a little bit of a scissor there. Let's make it. Scissor. A beautiful scissor. Yes. That cuts there and there. Those scissors, of course, are enzymes. So you have to find out what the enzymes are and how to program them to cut at exactly those places. So you have to find out where the place is. You have to make then the enzyme to cut in those places, which needs a certain temperature. So you find out temperature that these enzymes work the best to cut that off. And you have that little squiggly boy is now yours. That little blurb is now yours. You got that. Then you need to multiply that. Which you use other enzymes for. like we discussed Friday it was. This thing here on the top here. Let's see, there we are. So we got this messenger RNA stuff, which then went in, got the thing, and went out. That's the same thing will happen, but then with an enzyme we have to copy that enzyme into many little bitsies, many of them, and that needs another temperature. So you need the right enzyme, you need the right temperature, and then you get a lot of these little piece of genome, and then you can take a very big magnifying glass and see what they actually do. You can do all kind of research on them and see what it does. Perfectly beautiful magnifying glass over there. So this is basically what PCR does. So you have basically, for very simplicity's sake, you have a water cooker. Yes, a water cooker, like the one you have at home. Similar thing. Okay, that's the wrong way around. Let's do that the other way around. Turn you over. Let's turn the entire thing on, if I can actually select things. There we go. Rotate, flip. There we go. And we'll take a little bit of this one. There we go. Our little water cooker. Yes, because a PCR is a water cooker. A very exact water cooker for the exact temperature you want, an exact amount of time. You put in your little bit of the thingy. You put in the other ingredient, the enzymes. Then you're going to make sure the T is long enough, the temperature, in usually centigrade, because it's better than freedom units, and for a certain amount of time. That's the best writing of time you've ever seen, of course. And then you go to a different temperature, put in the next step, and so forth, until you have a lot of the same little genome pieces, and you can actually do either see if you can attach a certain enzyme to it, you can read it, you can do all kind of things with that. But that's PCR. And there's a lot of different work being done in PCR technology, because this takes time. As you can see, this all takes time to copy those things. And that is a very costly endeavor to have, well, very highly skilled people wait for stuff to work. So they want to try to increase the efficiency, make sure it reproduces faster, cuts faster, etc. And that's there's a whole thing in that. And these things can go for hundreds of thousands of dollars or euros to get one proper PCR machine. Yeah, so this is PCR. This is how you usually duplicate and do research on genetic material, but it requires a lot of knowledge. You need to know what parts you want to look for. You need to know how to make the cutting tool cut to the right places and not in between there or the wrong part out. And then you need to know exactly how to multiply that with the right enzyme here that actually will multiply that part and not any kind of snippets that are around, which they usually still do. And then you hope you get most of the bigger pieces, the piece you actually want to see about, and then duplicate them a lot. And then this you can, for example, put it into a virus. Just put it into a little virus boy and make it into a little what you call them? For example, insulin creation. There goes your little bits, and it goes into a bacterium who then makes insulin for you. As a small example. Yeah. So yeah, PCR. There it is. Beautiful. My chat, this is all for your knowledge, all for your brain. It needs to go into your brain, so open up your brain port. Open up your brain port, because here we go. There it goes, chat. Absorb the knowledge. Absorb it. There it goes. It's now in chat. Your brain has been filled with PCR technology. Yes. Anyways. Little side bit there. Now, where were we? Yeah. So I had a whole conversation. Where were we? Were we here? I don't know. I can see that. I can see where we were. Let's see, which one do align? So do you align? You align. You align. You. But you should be in there. Yeah, that should just about show. So there we are. And actually, that is yellow. So we were there. Bottom is yellow, so top is blue in this case. There we go. That's why I keep my template up there, so I can actually keep seeing what I'm doing. So this one, no, that's not the right one. That needs to be white. Yes. And then we need, oh, let's go. There we go. A little bit of PCR on how you do, how most people actually do research on genetics is by PCR technology. Because you just need to get a lot of the stuff so you can test it on a lot of different tests. Let's make this one smaller. There. Yeah, that seems better. I want to finish at least one now. At least one, right? At least one. The human genome codes for over 1,000 microRNAs. The human genome codes for over 1,000 microRNAs. I need to look into the microRNA, what you mean with those, because I know that the human genome codes for billions of enzymes, and every second you get you get genome transcription every second of the day. You get billions of excuse of that. So I think that number seems really small, unless you mean microRNAs is a technology we use to study it. Because I don't know what you mean with microRNAs. I mean, any kind of phage boy here or phage friend will have RNA in it, and if is the size in one of these is that what you call microRNA, or is that smaller? Because these are really small snippets that they usually put in. They can put in big ones, but usually it's just a little snippet they put in. So is that the microRNA you're talking about, or is it the technology that I'm missing yet? It's interesting stuff, dude. I like that. Here's my jam. I need to learn a lot more. I'm so far behind the technology. I'm old. I need to learn again, chat. My brain is to be put into action again. Need to learn myself things. I do not think that was just what the guys that got the Nobel Prize discovered. Okay. I do not think about it. Okay, let's have a look. I'm curious. The Nobel Prize announcements. Let's have a look. I'm curious. Tiny RNAs with profound physiological importance. Victor Ambrose and Gary Ruvkun discovered microRNA. They discovered this, okay. A new class of tiny RNA molecules. We know of the RNA molecules. There are these things right here. That's not the right one. This is the right one. The ones with adenine, cytosine, uracil, and guanine. That's RNA. They do not have thymine. That's only DNA. And these are usually found in as you know, in transcription. From messenger RNA who looks at your DNA and then actually transcribes it into RNA and then brings it over towards the place where proteins are being made. So mostly transport and towards the protein readers. And also in most viruses, phages are viruses, and many bacteria also have RNA. Not all, but many. So that's RNA. And that microRNA plays a crucial role in genetic regulation. The groundbreaking discovery in the small worm C. elegans. Hello, small worm. What do you look like, wormy boy? In this worm? Look at this worm. Oh, it's a nematode. It's a nematode. Yes. Okay. So a lot of research being done on nematodes because they reproduce fast. So we had this whole thing with genetics, right? A moment ago. The whole little test I gave you. This. We have a parent into generation 1, into generation 2, and so on. That speed between generations is important for research. The shorter speed, the better. So that's why they use a lot of fruit flies for genetic testing, because those have a very fast time from parent to sibling, from birth to next egg. The generation time is very short. Nematodes are similar, that they really fast reproducing. So you can have an egg within, let's say, a day, and a day later you can have an egg from that egg, you know? So it's pretty fast to get research done that way. Anyway, so they used that worm, which you can see right here, and they revealed a completely new principle of gene regulation. This turned out to be essential for multicellular organisms, including humans. MicroRNAs are proving to be fundamentally important for how organisms develop and function. This is confusing to me, because this is basically describing mRNA, right? Which we already know of. For those who weren't there Friday. Oh, it's all there. Be gone, Satans. Delete. So if we have 100%, no, there we are. So I can draw properly. So you have, let's make it very, very small. I'm not going to go into depth as I did Friday. You have the cell, and you have the cell core, the nucleus, and you have in the nucleus you have all your DNA. That's where DNA is all. DNA is just squirrely and being things. Now, outside of DNA, you have spots called ribosomes, which can make enzymes. They make enzymes. Now, enzymes do everything in your body. Those are your screwdrivers, those are your hammers, those are your nails, also your carpenters, because they do the things themselves. So these are the things that actually do things in your body, usually chemically. So, but you need, for these enzymes to be made, you need information from your DNA to get there and then be turned into an enzyme. So you have these little boys called mRNA, which I make with these things, which is way too big, but well, that's really, really big. Let's make it this. There. So there we go. That's our mRNA, do mRNA things. And he goes, let's put it there. mRNA, that's him right there. And he goes into the nucleus, goes towards a particular chromosome. And chromosomes roughly, roughly are 2 layers with different colored bits in between. I should actually make that big thicker. Let's make it that. So let's do that. Make it a there and there and there and there and there. They're the same size, but I'm not that good at it. So same size, and we have some green ones, actually red ones, right? Yeah, red ones. And that should also be red. There. Red ones. There we go. Some of those, and those are attached to each other. Blue with green, because that's how I use them. There, and there, and there. Not there, not there. That should be red. There. They have the same deal. Let's fix that one before I forget. There. Do that. They are the same size. I'm just bad at drawing. Don't ignore that part. So this is basically our DNA. The thing we've been making right now on screen for our emote, for example, right? And there. So let's just say our mRNA is looking for this code. It's looking for this code right here. Now we do have things, little enzymes that cut open the DNA. That are the scissors. They go there. It is a scissor. It goes in and cuts this open. It doesn't break it. It just cuts it open. So it will remove these bonds here and opens up a way, and the DNA will flow around it like roughly like this. Let's make the right colors again. There. So it will actually, with your DNA strength, this is that. And we have a little bubble, and we have a come together part again. So we have the scissor here. This is our little scissor. It's right there. Beautiful drawn. Beautiful scissor. Now we got our mRNA boy, which we had from over there. That mRNA boy will be right there. Okay, that's the wrong color. That's all wrong and incorrect and false. And there. Yes, and there. There he is. RNA boy, who is actually following that. Who's looking for that information there. And he's over here somewhere. And we also have here a little guy that is a zipper. Let's make that green, because why not? Who just puts everything back together again. And this is a little line that just keeps going past the entire chromosome, or for the parts you're looking for. So this guy will go, follow the scissor, go in here, and copy all this into RNA bases. It copies that information, and then goes away again, and goes outside towards these ribosomes I talked about before, and the ribosomes will see that and They will see that. And they will start making the enzyme that this codes for. That's what messenger RNA does. So it will just go hidden forth and make sure that he knows the information he needs to make an enzyme. Now, that is already let's see, completely new principle of gene regulation. This mRNA is already gene regulation. It's what a lot of RNA does, is regulation of genes. And there's also RNA that actually checks the DNA if there's any mistakes and tries to fix those mistakes. That's also RNA. And there's many other things happening over here to keep it all in working order. All the basic housekeeping things, that's also RNA. So I'm not seeing this special thing here yet. So I was hoping to see what the detail was, but so far, this is really bad design. You can't read it. You can't read it, can you? Really bad design there. But yeah. So I was hoping to find out what it actually means, but it's just that they have found completely new principle of gene regulation. But I was hoping to find out what the principle is. That would be nice to know, right? So let's see if we can find that. Can find the article about this. This is the article on there is a prize. Cool that you have a prize. Let's see what they have. Discovery of microRNA and its role in post-transcription gene regulation. So they found microRNA. So they found small RNA. And its role in post-transcriptional gene regulation. Okay. So we talked about transcription, right, last time? Transcription is right here. Right on top here. Where you have this whole thing. You have the DNA over here, adenine, cytosine, guanine, and thymine. And you have RNA, adenine, cytosine, uracil, and guanine. And you have these pairs, right? Where you always pair up, doesn't say it, you always have A and T combined. So if you look for here, so these colors here, let's assume that blue is A, then yellow is T, and then is this, let's call this C, if I can draw it there, and can I make a G there? It's very small. A G, there you go. So always when you have an A on this side, you have a T on that side. So also when you see a blue one, there is a yellow attached. So blue, yellow, blue, yellow, blue, yellow, right? And every time you see C and G attached, that's red and green, red, green, red, green, red, green, red, green. That is to keep this this size here same, so you can actually don't get a weird wonky knotted up problem there. Of course, my drawing is awful, so therefore this one is way too big and this one is way too small. But that's my bad. That's bad drawing. So they are always attached to the same nucleotide. So you get nucleotide pairs, which is A and T, and C and G. That's G, so let's get a C. There. That's always attached. But to transcribe into RNA, RNA does not have a T, it has a U. So A and U. And G and C just do the same thing as there. There. So to transcribe from this to that, you get something like this. You get A, T, C, G, for simplicity, will be transcribed into a U, because it will attach a U towards an A. It will become an A, because it doesn't have, because to a T you also connect an A, and it does have an A, so it will make an A over here. The C will become a G, and the that's bad. It should be a G there, and that should become a C there. So this is your messenger RNA. This is what transcription is. This is from one to the other. This is our DNA. So your DNA goes into messenger RNA, it will transcribe. This is transcription here. And they say they found something... not there. The role in post-transcriptional gene regulation. Now, there are many things that we don't know much about, that I don't know much about especially. So, we have here, for example, we do know that mRNA swims around, goes in, finds a part, and brings the part back to a ribosome. We don't know why this mRNA goes in, or when it goes in, when it goes look for what part on the genome, what chromosome it will attach to, why it goes there. And we don't know when it goes back. We don't know how it regulates the amount of enzyme made over here. So I assume, since they talk about post-transcription gene regulation over here, so I would assume that with transcription being done here, it could be that they will block, for example, some mRNA to regulate enzyme production. Because some enzymes are more important than others, some you need more of, some you need less of. Well, they're all important. Also, this is the best kind of writing ever. But sure. So, it could be that it just holds up mRNA and just says, hold you, stop the engine. It's like, no, you cannot pass for a bit. Or it could actually accelerate them. Or it could check if their transcription is proper. Maybe the transcription, there can be mistakes happens here sometimes. And it just checks if it's good transcribed. Could be many things we don't know yet. Or at least as far as I know, we don't know yet. So let's see what else we can find about this. This year's Nobel Prize honors two scientists for discovery of a fundamental principle governing how gene activity is regulated. So we got gene activity here. Okay. Genes are not active, by the way. It's just a nice word, but doesn't mean anything. The information stored within our chromosomes can be likened to an instruction manual for all cells in your body. It's more an instruction manual for all enzymes in your body, but sure. Every cell contains the same chromosomes, so every cell contains exactly the same set of genes and exactly the same set of instructions for each individual. So all your human cells have the same genes in there. There's of course some mutations in there, but overall 99% of all your cells have the same genes. And the other ones have just a little thing broken in them. Yeah, different cell types, such as muscle and nerve cells, have very distinctive characteristics. True. They have the same book of knowledge, but they use different parts of it to become a nerve cell or to become a muscle cell in this case, right? Yeah, muscle cell. How do these differences arise? The answer lies in gene regulation, which allows each cell to select only the relevant instructions. It ensures that only the correct set of genes is active in each cell type. Okay, that's kind of self-explanatory there. So you get a whole row of books here, a row of books there, and let's actually do that. A big book, and another book, a very big book, and we just take that a little bit. Oh, then of course the black doesn't work, right? I mean, no, it doesn't work. Does not work today. Let's do this. So got this here, a few more books. These are DNA. Another representation of DNA. And these are whole books, so these are not just one gene each. Or one nucleotide pair. These are complete books of thousands of genes together. Chromosomes are scarily big, by the way. Scarily big. Did you know that chromosomes, if completely rolled out, one chromosome, completely stretched out, is about 2 meters long, roughly? 2 meters long in every, and that's just one chromosome of the 40, now I have to say the right number, 46 you have in each of your cells. That's what, 90, 46 times 2 is 92? Yeah, 92 meters in every single cell packed in your body. Yeah, that's kind of, yeah. That's is a lot of info. That's a lot of info. The amount is stupidly scary. Anyways, there's some books. And we're looking for a muscle. Actually, no, let's make that. That needs to be black still. Also, black. And you, let's become red. We'll make a few red books. Oh, no, okay. Apparently not you. And we'll take a few purple books, so we have some different colors, because I always use red. No, that one. That one also not. It's in fact so. Let's say this one here. Let's fill that with the same color. Bam. And we do the same thing here. There we go. Black and white. And here we have a nerve book. And a muscle book. Muscles. So, this of course your genome is your full set of chromosomes, DNA. So, every cell has the complete set of DNA, so they have the complete works of everything. But yeah, if you're a nerve cell, you need to get the nerve books out and need to make the nerve books work. But you don't want to activate the muscle books. So neat. How to find out which ones to activate, which one not to activate, is a pretty big unknown. And they apparently found a part of that. So that's how the differences, the differentiation between cells, how that is a problem. The enzyme lies in gene regulation, which regulates which books being picked, which allows each cell to select only the relevant instructions to ensure that only the correct set of genes active in every cell type. Yes, true. Sorry about that. Victor Ambrose and Gary Rupkon were interested in how different cell types develop. They discovered microRNA, a new class of tiny RNA molecules that play a crucial role in gene regulation. The groundbreaking discovery revealed a completely new principle of gene regulation that turned out to be essential for multicellular organisms, including humans. It's now known that the human genome codes for over 1,000 microRNAs. Okay, what does that mean though? I mean, I don't want to know what is a microRNA. Is that an RNA beneath a size of X for 15 lengthwise? What is a microRNA? A surprising discovery revealed an entirely new dimension to gene regulation. MicroRNAs are proving to be fundamentally important for how organisms develop and function. But how are they different from messenger RNA or other RNAs? Why do they get new classification? I want to know this. Essential regulation. Oh, there we go. Cool. This is also how you see what things do. So you can have 20,000 genes. That's on all your DNA. So this is divided over your... this is 20,000 genes. Let's assume that it's divided over one set of your chromosomes, over 23 chromosomes, and you have a duplication of that. So you have 20,000 genes, and then you have 20,000 copies, I assume. It depends on how you look at genes, because you do have genes here. Not that one. Not that one. We need the word for that. Word, there you are. Hello, word. So we have these genes here. These alleles here these are genes. This is a gene for, in this case we call it hair color here. This is all hair color on 2 different chromosomes. Do they count that as 1 gene or 2 genes? Because it is 1 gene, it's just we have a duplicate of it. So is it actually 40,000 genes? Or is it 10,000 genes with 10,000 copies? Curious about that one. Anyway, you got the gene, you got transcription to our mRNA, which I just described in the file over here again. So that's the whole changing the letters up, or we also did that over here. In this one here, where we go from A to U, C to G, and so on. So this here, this little part here. That's what they show off there. Goes to protein. So this is done in a ribosome who makes the protein. So mRNA, from DNA to mRNA is transcription. From mRNA to protein they call translation. Yes. So mRNA goes to a ribosome, which then translates it or produces or makes the protein. Okay. Then becomes a cell type. Yeah, that is roughly correct. It's a bit simplistic, but it's roughly correct. So, okay. So I was hoping to find some more in depth here. This year's, yeah, or organs, tissues, no. Let's see. Genetic information flows from DNA to messenger RNA, mRNA, via a process called transcription, and then to the cellular machinery for protein production. Their mRNAs are translated so that proteins are made according to the genetic instructions stored in DNA. Yeah. Since mid-20th century, several of the most fundamental scientific discoveries have explained how these processes work. Yes, because that's a very complex process. With many different cell types, all identical genetic information stored in DNA. However, these different cells express unique sets of proteins. How is this possible? This is their question. This is a question they want to ask. How is it possible to differentiate one cell or a different cell in when you're creating an organism? You want to know, hey, will this become a foot or will this become a brain cell? You know? Well, brain cell, foot, head or foot, you know? The answer lies in the precise regulation of gene activity so that only the correct set of genes activate each specific cell type. Correct, so that's the picking of the correct book. This enables, for example, muscle cells, intestinal cells, and different cell types of nerve cells to perform the specialized functions. In addition, gene activity must be continually fine-tuned to adapt cellular functions to changing conditions in our bodies and environment. True. So, for example, when you go outside, fresh air, you touch grass. Now you're cold. Your body's like, oh, I'm cold. I need to start doing things. I need to start producing sweat. I need to reduce producing sweat. I need to increase production of fat to get a little bit of layer on top of your skin. You need to start shivering, so your muscle cells need to actually modify themselves to start moving, which is a modification of the cell itself. It's not just a program happens, it just the cell has to actually modify itself for your muscles to move, etc. So yeah. So that's all done with regulation. If gene regulation goes awry, it can lead to serious diseases such as cancer, diabetes, or autoimmunity diseases, or many more things. Therefore, understanding the regulation of gene activity has an important goal for many decades. True. In the 1960s, it was shown that the specialized proteins known as transcription factors can bind to specific regions in DNA and control the flow of genetic information by determining which mRNAs are produced. So you already have specialized proteins, transcription factors, that bind to specific regions in DNA. So we come back to the part where we had the, I think it was paint. No, it was Word, I think. No, that's too big, it's too high up. No, it was paint. It was paint, my bad. Paint here. So you have some, put it away. So yeah, we got ourselves the scissors here. If I still have scissors, I removed there's scissor. There's one. So that scissor will not just willy-nilly cut in everywhere. It will cut in the correct place. To cut in the correct place, you need a protein. It also is a protein that cuts, but also has a protein that says you need to cut here. Now that protein is what we're talking about here.
That's what they call transcription factor. Is that so? The scissors are or have either one of them transcription factors, which tells them, hey, you need to start cutting here. That's what it is. So is their tom-tom. There's their tom-tom transcription factor. And it was believed that the main principles of gene regulation had been solved. However, in 1993, this year's Nobel laureates published unexpected findings describing a new level of gene regulation, which turned out to be highly significant and conserved throughout evolution. So they found something new there, yes. In the late 80s, Victor Ambrose and Gary Ruvkun, the two Nobel Prize winners here, were postdoctoral fellows in the laboratory of Robert Horvitz, who was awarded the Nobel Prize in 2002 alongside Sidney Brenner and John Stilson, so even more Nobel Prize from the same place. In Horvitz's laboratory, they studied a relative unassuming 1 millimeter long roundworm, C. elegans, that's a worm here, there you go. Despite its small size, C. elegans possesses many specialized cell types such as nerve and muscle cells, also found in larger, more complex animals, making it a useful model for investigating how tissues develop and mature in multicellular organisms. True. Ambrose and Ruvkun were interested in genes that control the timing of activation of different genetic programs, ensuring that various cell types develop at the right time. It's important to develop at the right time, because else your placement will be wrong. If a baby develops, they develop usually along the spine, roughly, and things can attach to that. If you have first a leg would start growing, an arm would be growing, but there would be no spine to combine the two. They could be on any part of the body and then would not be functional, because on the wrong part of the body their orientation would be incorrect. So therefore timing is essential to decide what to make when. Let's see. They studied 2 mutant strain of worms that displayed effects in the timing of activation of genetic programs during development. So Lin4 and Lin14. And I want to identify the mutated gene and understand their function. Ambrose has briefly shown that in the line4 gene appeared to be a negative regulator of the line14 gene. That means that the line4 gene says if you make more if line4 gets red and gets made into an enzyme, the resulting enzyme will make sure that there will not be too much more made of Lin14. To either bind to that part of the genome to stop it from being cut, or it will do other things that make sure there's less Lin14. So Lin4 is a brake towards Lin14. However, the Lin14 activity was unknown. However, how the Lin14 activity was blocked was unknown. So don't know how it blocked it. It could block the scissor from going there. It could block the place for the scissor to attach to. It could do many other things to block it. So you just don't know how. And they were intrigued by these mutants and their potential relationship and set out to solve these mysteries. Okay, so here we go with the mutants. There's the guys, the winners here. Gut, muscle, nervous system, one of the worms. Normal mutant, line 4 mutant, line 4 mutant, line 14 mutant. It seems like normal. So I assume just the literally size of the creature itself. Also, you see weird speckles in the body there, which seems odd, seeing that this roundworm is kind of smooth. Here's weird speckles. And this one's also, it seems like this one is, I'm not sure this one is dying. It looks bad. Anyways. Also they have 100 billion? Is it billion in American? I'm not sure. I'm not sure if it's billion in American. Billion and trillion are a bit weird in American. At least in Dutch it would be a billion. 100 million. Yes. Actually no, it's 1,000 million, it's a billion. Yeah. 1,000. Oops. Oopsie. So, let's see. The model of the research, they analyzed the Lin4 mutants in his newly established laboratory at university. He got a new laboratory. No, 100 million. Not 1,000 million. Yeah, you're right. Yeah. Those numbers usually confuse me. Those are big numbers. They don't fit in my brain. My brain's small. Anyways. After his postdoctoral research, Victor Ambrose analyzed the Lin4 mutant in his newly established laboratory.
Methodical mapping allowed the cloning of the gene and led to an unexpected finding. So methodical mapping is what we did over here, right? Actually, it's gone, right? It's our PCR thing, where you actually need to find what part of the genome, which they do as well, what part of the genome you need to cut into. That's the mapping. That's a very difficult part of gene research, where to look for them, because genes are enormous, stupidly big. So what part do you need to start cutting is a very big part of science. So that's what he done over here. So they found a gene and cloned it, which they did probably using PCR, which I show you before. The little water boiler. And led to an unexpected finding. The Lin4 gene produced an unusually short RNA molecule that lacked a code for protein production. So this RNA is too short or doesn't have a code for protein production, so it cannot attach to a ribosome to become a protein, or to be translated into a protein. So this is definitely not a messenger RNA. That's what it says here, because it cannot make protein production. These surprising results suggest that a small RNA from Lin4 was responsible for inhibiting Lin14. But how does it work? Normally, as I said before, in the body, everything is done by proteins. Proteins are your screwdrivers, your hammers, your nails, all those things are proteins. Apparently, this RNA does a similar function. It is a tool on its own instead of making a tool. If you get that. So this RNA, which all RNA normally is just information going in the fourth, and that goes in the fourth is done by enzymes attached to them usually. That's why with the virus boys, the virus is the guy that actually sent it in. But there's a little bit of enzyme attached to actually make it go somewhere. But this RNA probably also has some kind of protein attached, so it does go somewhere. Or it might be passively just floating around. Sometimes that happens, is enough. This one actually performs a function that is not just reading and writing. It actually does something else to inhibit Lin14 making. So it actually is already a break on its own. So they investigated the regulation of Lin14 gene in his newly established laboratory. They do love to say about his newly laboratory. Oh wait, he got a new one as well. Newly established laboratory and a newly established laboratory. They do want to show off that they have laboratories now of their own. Yes, they're proud of them, which they should be, but still, very proud. This is that's all very interesting. Oh, is it the same place? Isn't it also? Oh, university and Harvard Medical School. Okay, so they're different places. Unlike how gene regulation was then known to function, Rifkin showed that it is not the production of mRNA from Lin14 that is inhibited by Lin14. So it's not the mRNA that's being blocked. The regulation appeared to occur at a later stage in the process of gene expression. So you have this mRNA going forth and grabbing Lin14 from the DNA. It swims in and grabs Lin14 information. And then normally it would go to a ribosome to be made into an enzyme. Apparently, Lin4 goes in between that and says, "Halt! Stop! Don't do this." Somewhere along that line. And that's the mRNA, sorry, the RNA itself, the microRNA in this case, and not just an enzyme made by it. The regulation appeared to occur at a later stage in the process of gene expression, though the shutdown of protein production. So it stopped protein production. So it could be something that does something to the ribosome itself. It says, "Do not accept this man." Basically, this would it be a wanted poster? Do not accept this man or this mRNA. Do not accept it. Okay. Experiments also revealed a segment in Lin14 mRNA that was necessary for its inhibition by line 4. So in the mRNA Lin14, there is a spot in it that allows for attachments to Lin4. So you have your mRNA, and I'm just trying to understand this as well, so it's new to me as well. So you have your mRNA just doing mRNA things and just wrap it up. I'm an mRNA. I have my information. Okay, that's not good. I have my information. Wrap it up. We have a break, because I also have a break. And some spot here, right there, This is Lin 14. Best 4 ever in existence. Lin 14 mRNA. And they have a specific spot here somewhere, probably on the thing itself, not on the information. This is what I usually show as information. It's somewhere there, not there. Ignore that one. That cannot be there, because this is then the information. That's how I draw it. It's not correct. It's how it shows, but that's just I want to be consistent. So somewhere there is a spot where Lin 4, which is not a messenger RNA. So let's make that green. Is it visible? Is green visible? Kind of. There's Lin 4. That's... Lin 4 here goes forth, attaches there, and blocks off that mRNA from something. Maybe from attaching to a ribosome. Maybe stop it from moving altogether. It does something to stop that. We haven't gone that far yet. And the two guys compared their findings, which results in the breakthrough discovery. The short Lin 4 sequence matched complementary sequences in the critical segment of the... So should the short Lin 4 look the same as critical segments of Lin 14. So they both had a set of, let's call it coding, and let's say they had a very important part that says, I don't know, 1, 2, 1, 1, 2 on you, but you also have a segment that says the exact same thing. 1, 2, 1, 1, 2. So they have an exact same set here of information. Doesn't matter what the information is. Okay. They performed further experiments. Oh, dang it. I need to go. God, I don't want to go. This is cool. I want to see more of this. Damn it. Damn it. I need to go. I don't want to. Trust me. Trust me. Help. I don't want to go. I want to read this. I want to understand this. This is cool. I need more of this. Well, at least we found out for today. I know. I need to go to the store. My parents will be on the front door soon, because or local supermarket got placed away, so we have to go by car. So we carpool for that. So yeah, I sent you down a rabbit hole. You did, but I like it. These are the cool rabbit holes. These are awesome. I'm gonna put this in there. Yeah, let's not hack this side. Let's make this a new one. Another folder. And we need more. New folder. How do we call this? Nobel Prize. Trust no one. There we go. There we go. Nobel Prize trust no one. We will continue this tomorrow because I want to know more about it. I want to know how this works. This is cool. This is cool stuff, man. Oh yeah. Also, look how happy he looks. He looks happy. Yeah. Happy scientists. Good. Anyways, we will continue this tomorrow, unfortunately. I want to continue on! Anyway, tomorrow. Chat, we must have patience. I must have patience. I shall be patient. Tomorrow we draw more paintings, and we keep forgetting to make this. Yes. Anyway, I showed you a little bit more information, a little bit more genetic stuff. I hope you liked it. I hope it was fun. A little bit of a challenge there. You saw my family. This is my family. Hello, family. And that I can get infarcts. Yes, very fun. Yes. Anyways, and we've done some Nobel Prize stuff, and I mean, it's a cool day. It's a good day. Dudes, I thank you very much for watching. I hope you enjoyed. Hope it's fun. Camploy, you're awesome. Anyways, I'll be back tomorrow. We'll be reading more into the Nobel Prize thingies, because I want to know more. I need to know more. And if you want to know more, I'll see you tomorrow. Goodbye. I still don't want to. I want to read more. Shall I cheat and read more already when I get home? But you're right, the shopping must be done. The shopping must be done. I'll see you tomorrow, guys. Cheers and trust me. Thanks for bringing this to me. I think it's awesome. Goodbye.